curiosity, how many of you have actually touched Clojure before now? Anybody touched it at all? Okay, that's fine. I don't assume any pre-knowledge of Clojure for this talk. That's why it's called the Curious Clojurist. And I'm here to talk about Clojure. And the things I want to talk about are what I'm calling the 4 elevators of Clojure, the thing that really elevate it above all the other languages on the JVM. And here are the 4 elevators: Java interop, Lisp, functional programming, and Clojure's unique take on state and concurrency. There are lots of languages on the JVM now. Does anybody know how many languages on the JVM now? Just out of curiosity. Anybody? Anybody take a guess? I'll bet you're an order of magnitude off if you guess. 20. So they're more than 200. So I was right. You're more than an order of magnitude off. There are more than 200 languages in the JVM right now. So why should you choose one like Clojure versus all the other ones? Well, that's what I'm going to attempt to answer during this talk. So here's the one-line elevator pitch for Clojure. Clojure is a dynamic, strongly typed, functional, high-performance implementation of a Lisp in the JVM. So let's talk about a few of those characteristics. Clojure is dynamic, meaning that it is dynamically typed like Ruby and Groovy are dynamically typed, meaning that you don't predefine the type of a variable, but once you assign something to a variable, it is strongly typed. It retains knowledge of that. You can do reflection on that thing. You can do any kind of activity you want on it based on the type. So it is dynamic, strongly typed. So in that way, it is like Groovy and Ruby, both of which are dynamic, strongly typed languages. A difference, though, between Ruby and Groovy and Clojure is that Clojure is heavily functional. And this is a really big difference between Clojure and a language, for example, like Scala, which is also a functional language on the JVM, but they are actually very, very different in their approaches, because one of the things that Scala is trying to do is build a bridge from the object-oriented imperative world to where it thinks you should be, which is the more immutable functional world. But the way that they're doing that is supporting both paradigms, which is a really nice characteristic for a bridge, but it's also a dangerous language to program in because you have to have extreme discipline to do the right thing. Same thing happened in C++, which is also a multi-paradigm language. People had a mishmash of C and C++ and objects and procedures and functions. The same thing is true in Scala, which is a multi-paradigm language. Clojure is not a multi-paradigm language. Clojure is a functional language first and foremost. Now, it can interact with all the imperative Java world, but you don't really write imperative code in Clojure. You write functional code. And so it has a much stronger opinion about the way that you can do things correctly. And in fact, Clojure has taken over a few things from you, but by doing that, they've greatly simplified some really, really tricky things in the JVM. So for example, Clojure does for concurrency what Java did for memory management. You can write thread-safe code in Clojure without thinking once about threading, and everything is automatically concurrent and thread-safe. And I'll show you what that looks like. So it's a very functional language and a single paradigm language versus a multi-paradigm language. It's also very high performance, one of the goals in Clojure. This is actually, I think, Rich's 5th Lisp implementation. So he knows how to do efficient Lisp implementations, and one of his goals was to make a really high performance language on the JVM, and he has managed to do that. In fact, done so in some ways that are a little bit controversial in the Lisp world, because the traditional way that you build Lisp programming languages is a particular data structure called a console. Rich decided not to do that so he could make a higher performance version in Java. And so the surface characteristics of the language are unchanged, but the internal implementation is different so that he can get really good high performance. And the last thing here is that it is a Lisp on the JVM. So isn't Lisp the one with all the crazy parentheses? Yes, it is. Which brings up kind of an interesting point. People don't like to read Lisp code because it looks like it comes from another planet. And so you would have to build a brand new language and use Lisp syntax on the JVM, you've either got to be a crazy person or you've got some really cool ulterior motive. And I've met Rich. He's not a crazy person. He's got a really cool ulterior motive because Lisps have a characteristic that other languages just don't have. And the way that that's captured is by saying that Lisp is a homoiconic language, which means that Lisp programs are actually also legal Lisp data structures, which doesn't sound like that big a deal. It turns out it's a huge deal. when you get to really, really complex things that you need to attack in your language, this makes all the difference in the world. So Lisp programs actually consist of Lisp data structures, and this is all kinds of useful, and I'll show you implementing macros and why this is all kinds of useful and why it is worthwhile enduring the pain of learning to deal with the parentheses. And the pain goes away really fast, trust me. It looks like it'd be painful for a long time. It's not at all. There are some really compelling reasons to fight through that and adopt this language. So let's talk briefly about the ecosystem. I'm not going to spend a lot of time here, but if you have a new language, you need to be able to do stuff with it. So the language itself is on Clojure.org. It's an open source language project. It is maintained by Clojure Core, and so if one of the things that you strongly desire when you pick up a new language is to have a throat to strangle if things go wrong, then Clojure Core will sell you a throat to strangle if something goes wrong, if you want support for Clojure or things around Clojure. So there's an ecosystem, a la the Spring ecosystem has grown up around Clojure. There are a variety of different ways to edit Clojure code. If you're a typical Java developer, you're probably in Eclipse, and so there's a Eclipse plugin called Counterclockwise that gives you syntax highlighting and REPL and a bunch of other nice things. If you want to go more traditional old school in Emacs, there's an Emacs starter kit for Clojure that gives you all the bits and pieces to get Clojure up and running inside Emacs. There's also a really nice IntelliJ plugin that does a Clojure. The build tool, there are several in the Clojure world. The most popular one is Linigan, which is, this is actually based on a poem about this guy fighting an army of ants, which is where the name of this tool came from. There's also a tool called Cake, which is rake in Clojure, but this is the most popular one. This actually does transitive dependency management, kind of like Maven, but without the evilness of Maven. So it does the transitive dependency management for you, but the syntax, of course, is all Clojure code instead of XML. And it has the usual complement. There's a web framework. There's several. The most popular web framework is called Composure. It's a very lightweight, basically just router framework a la Sinatra in Ruby on Rails or Ratpack in Groovy. There's also several different ways to talk to relational databases. There's CLG Record, which is a partial port of the Ruby active record stuff that's in Rails onto the Clojure stack. There's also Clojure QL, which is relational algebra to SQL as a DSL. Excuse me. There's also Clojurist, which is Clojure implemented in JavaScript. So they've actually written a Clojure interpreter in JavaScript, and you can run Clojure code on top of JavaScript using a couple of key libraries like the Clojure library from Google. But you can now, it doesn't support everything because there's some things that JavaScript can't support, like the software transactional memory stuff, but all the syntax is supported, so there's a really nice opportunity here for people to write the same code on the back end and the same code on the front end and pass data structures back and forth because you've got Clojure on both the browser and the server side. So speaking of code, let's look at and see what some Clojure code looks like. Clojure has the typical kind of data types you would expect on a JVM-based languages. We have strings, which are double string delimited. We have characters, which are delimited with a slash in front of them. We have regular expressions as well. And this is a good example of some of the nice things in Clojure. The regular expression here maps directly down to the pattern class in Java. So this is really just a wrapper on the pattern class in Java. You can also get to the matcher, but Clojure doesn't like matcher because matcher is mutable in Java, which is an evil thing for matcher to be mutable. And so Clojure's implemented their own implementation of matcher that's not mutable, which is a good thing. We have precision integers. And you'll notice that these can be represented as ints, longs, or big integers. You never have to think about this in the Clojure world. It automatically escalates to the correct data type for you. So if you do something that's going to overflow an integer, it'll just roll over to a long for you automatically. We have doubles and we have precision doubles, which are represented by big decimals underneath. We have booleans, which are represented by booleans underneath. We have nil, which is Clojure's version of null. We also have a symbol type. Symbols are basically strings that represent things like operators or function names. There's also a specialized symbol called a keyword. This is not like a keyword in Java where if and while are keywords. These are basically, from an implementation standpoint, in-turned constant strings. But this keyword foo will always represent this value of foo. And so it's useful to use these for efficiency's sake because rather than use strings. And there are several data structures in here that kind of expect keywords like maps. Keywords are frequently a key part of the key value store. So let's look at some data literals. We have lists, which are singly linked and insert at front. And the example is that it's just within parentheses. That's a legal list in Clojure. But Rich actually added a new kind of sequence data structure to Clojure called a vector. And this is indexed insert at rear. These two exist because they have different performance characteristics. In some cases, you want to use a singly linked list. In some cases, you would like to use an indexed vector. He also introduced vectors and with a square brace syntax to clean up the syntax for defining functions. He uses a vector instead of a list, and that actually gets rid of a really nasty set of internal parentheses that you'd like to get rid of. I'll show you an example of that in a second. We also have maps, which are key value pairs. Keywords are frequently used here, but any Clojure class can be used here as a key. You don't have to worry about the same thing you have to worry about in Java, because everything here in Clojure is immutable. And so that everything makes good map keys, because that's the thing that you have to be careful in Java. Don't let mutable things be map keys, because if you mutate it, then you won't be able to find your entry anymore. That's not a problem here in Clojure because everything is immutable. And we also have sets, which have this syntax with a pound sign and curly braces. This is, Clojure is very characteristic of a lot of functional programming languages in that it has very few data structures, but a lot of operations that understand those data structures. A lot of imperative object-oriented languages have a lot of data structures and a lot of operations. Most functional programming languages have a very small number of data structures, but a lot of things that operate on those data structures. So let's talk about function calls. Here's what a function call looks like in the Clojure world. All you're really doing here is taking the paren, which you'd normally put right here in front of hello, and just scooting it out to be in front of the opening paren. And so that's a function call, and its argument is a single string called a hello world. But you'll also notice that this function call is a legal Clojure data structure, because it's just a list. It's a list that has two elements in it. It's a list that has two symbols in it. This is part of that homoiconicity that I was talking about before. Here's how you can define a function. Def in a greet. You can put a doc string there if you want, which is a string that comes back. Clojure has a tool called the REPL, the read eval print loop, where you can start it up and play around with Clojure code. One of the functions you can call is doc for something to get documentation for it, which returns you the doc string. That's optional, but you can put it in there, and you can also do more elaborate kind of JavaDoc style documentation if you want. The arguments in Clojure end up in a vector, so it's function name, and then this is a comma delimited list of arguments, actually comma or space delimited. And this uses a vector instead of an embedded list, which lets the function definition stand out a little more. And then this is a function body, which is going to be a series of function calls. But again, this homoiconicity property pops up. Notice that all these things are just the data structures we've already seen. It's a list that has a bunch of symbols in it. There's a vector, and then there's another list with a bunch of symbols in it. At the end of the day, it's all just data. And the reason that's important will come up in a bit. Yeah? Are the new lines significant? No. No space is significant. In fact, a comma in Clojure is also white space. So you can put commas anywhere you want to make it look prettier. I said comma delimited list here, but it doesn't matter. It can be space delimited because it doesn't matter. So space is irrelevant here. In fact, even less so than in a lot of languages. And that's part of this, all the parentheses stuff. You can also, for some interop scenarios, you want to be able to prefix function metadata, like types on here. And so you can do that if you want. That can either be a type or an arbitrary map that has a value in it. So you can add type hints here, particularly for Java interop. If you have an overloaded Java function and you want to make sure that you call a specific one that has a particular type signature, you can by applying function metadata, but that's never really used in the Clojure world. So speaking of Java interop, one of the things that you're obviously going to need to do in a JVM language is interoperate with Java. And so let's look at Java interop and what that looks like. You have syntax extensions to reach all of Java. So there's no part of Java that you can't get to in Clojure. Clojure also compiles to bytecode. So this is not an interpreted language. It compiles down to bytecode, so which means it's fast. And you can also call Clojure from Java if you want, because at the end of the day, it's all bytecode. The thing you run into is that Clojure is expecting some characteristics of the things that it deals with. Like it assumes immutability. And if you pass mutable things over, you can still interact with them, but it's not a natural kind of thing to do. And calling Clojure from Java makes a lot of assumptions about interfaces it's implemented and a lot of other things that make it difficult. So if you want to see a good example of that, Venkat Subramaniam has a new book out on concurrency on the JVM, and he shows an example of calling into Clojure software transactional memory from Java. So it is possible to do that, but there's a long checklist of things you have to make sure because Clojure is a much more restrictive language than Java in terms of some of the things it will allow. So if you want to construct a new widget, you would fire the constructor like this in Java. In Clojure, everything is function-based. And there's syntactic sugar in the language to say if you want to fire the constructor on something, just do class name dot and then argument list, constructor parameter list. You can also get to static members. In Java, you would do class dot. In Clojure, you do class or namespace slash and whatever the constant is. You can also get to instance members. So if I want to get to random number next int, the way to do that in Clojure is dot next int for random. So notice that instead of being object function, it's function object everywhere. And then any additional parameters would go after the object that's there. So any dotted method you can call like this in the Java world. But there's a really common idiom in the Java world I like to call the law of Demeter violation, where you say this, or this, get this long series of things. And that would be really ugly in Clojure because it would have to be inside out. And so there's syntactic sugar in Clojure to allow you to do chained access. And so if you're calling person.getAddress.getZipCode, you can just put dot there, and then anything you put in here, there's an assumed dot in between all those guys. So this can be as long as you want. Dot handles all the intermediate dots there. Yeah.
So I'm not sure this is correct or not, but this is running on top of Java, on top of the JVM.
On top of
a model where you could actually have a scripting language that kind of skips over the Java intermediary and actually just runs on top of the JVM?
Well, this does. This does not produce Java code. This produces Java bytecode. When you compile this produces bytecode just like Java. Yeah. This is not doing code gen in Java. This is pure Java bytecode. So
the Groovy, like I've used Groovy in the past, and Groovy does compile down into Java then into...
Well, actually, Groovy doesn't do that anymore either.
None of them compile to Java code.
Yeah, they all compile to bytecode. Now, some of them are interpreted. So JRuby, for example, is interpreted, but Clojure is not interpreted. It compiles straight down to bytecode. So
the earlier versions, I guess, of Groovy that I used created a Java class that got compiled and then ran.
You must have been using Groovy pre 1.0 because that would have been ancient times. Because I mean,
last 4 years?
Not unless you've got some weird build of Groovy, because Groovy has been a first-class language for a long time. So, but I mean, there may be some sort of translation tool that's doing that or something, but this one does not translate to Java code at all. This is straight to bytecode, so very high performance.
So it's always 2 dots, no matter how many.
Yeah, it's always 2 dots, no matter how many you want. That just basically says put dots between every one of these things I'm about to chain across here. So. And in fact, one of the things that terrifies people about Lisp is the number of parentheses. But from the Java code that we've seen so far, let's count them up. And so in the Java version of the code that we've seen so far, we've got 8 parentheses. In the Clojure version, we've only got 6. So there. Clojure realizes that the parentheses can be cumbersome, and so they have a lot of syntactic sugar in the language to get rid of situations where you'd have to go nuts with parentheses, things like dot to simplify some of those strings. So this actually line has fewer parentheses than that line. So as I said, you can get to all the pieces of Java. So for example, let's say you wanted to implement an interface from the Java world. That's easy. There's a function in there called reify. You give it a Java interface, and now you can have method bodies down here. What does what does runnable look like? It takes a single run method that takes no parameters. There's a single run method with no parameters. There's the body of the method. If this interface defined multiple method signatures, then I can have multiple bodies down here with multiple methods, each one with parameter signatures. Certainly, using Clojure changes the shape of your code. So what I want to do is take a common piece of code that probably exists in your code base right now, Apache Commons, the isBlank method, and convert that over into Clojure kind of one step at a time, deconstructing it from one language to the other. And I'll do this a couple of times. Here's the first time. So there's this blank. This is from Apache Commons. What this does, you pass it a string, and it tries to figure out if it's blank or not. The way that it does that is check to see is it null or is it length of 0, then it returns true. Otherwise, it goes through every character and looks to see if it's white space or not. Well, let's convert that over to Clojure. First thing we'll do, since Clojure is dynamically typed, we'll get rid of all the type information. So we'll strip out all the types. Looks like that. We're definitely in pseudocode now. We're between Java and Clojure now. We can get rid of the class because we don't need classes here. Everything's function-based. The next thing we're going to do is use a higher order function. So this thing right here, this for loop, basically I'm going to replace it with an every function that says for every character in string, then tell me if it's white space or not. So that's a higher order function. Now I'm going to come in and get rid of the corner cases. It turns out that my every handles null and 0 linked strings correctly, so I don't need that special guard condition to handle that case. So I can get rid of that corner case, which leaves me there, and now I can Lispify it. There's what is blank looks like in Clojure. And that one is a lot easier to read than the Java version. Even if you're not a Clojure developer, I think that one's way easier to read because even if you're an experienced Java developer, if I didn't show you the name of that method, it would take you 30 seconds, 45 seconds to figure out what that method does. Whereas here, blank is that every character is white space. That's almost English. That's actually one of the goals in Clojure, is to be able to write code that is very, very readable code. And this is very readable compared to this stuff, because that stuff's a bunch of loops and other arcana. This is a pretty clean version of is blank.
Is the question mark character there significant, or is that just a naming convention?
It's a naming, I'm glad you brought that up. It's a naming convention in the Clojure world that suggests that this returns true or false. In the traditional Lisp world, you put a P at the end for predicate because the languages wouldn't let you use punctuation for function names. But you can use question mark as punctuation for the function name. It is part of the name, and that's a clue that it probably returns true or false. It's not a requirement, but it's a convention. That's a good question as well. So this is actually a syntactic sugar for anonymous function. So what every does, every takes in a function to apply to each element. And so this is shorthand for saying, I've got a function, but it only takes one parameter. So I'm not actually going to create function with one parameter and give that parameter name and then call it. So this is the placeholder for the single parameter this thing takes. So if you have a function that just takes a single parameter, you can write it like this as an anonymous function. Yep, exactly. You can also, if you have a function that has a bunch of arguments and you don't care about some of them, you can use underscore to basically say, I skip those, I don't care about those. So what's so special about Lisp? I've been bragging about how special Lisp is. This is a chart that Paul Graham came up with. Now, Paul Graham's a big advocate in the Lisp world, and he wrote a book called Hackers and Painters. And one of the articles in Hackers and Painters is called Beating the Averages, where he talks about the relative strengths and weaknesses of various programming languages. And this is his chart, where the industry norm languages like Java and C#, et cetera, have conditionals, variables, garbage collection, and recursion. No big deal there. The kind of cool kid languages, the Rubies, the Groovies of the world, have added some more stuff. A function type, a symbol type, the whole language there all the time, which means you have the ability to do metaprogramming and control the runtime characteristics of your language. Everything's an expression, but this last one, this homoiconicity, only Clojures end up with this one. So let's talk about that one a little bit more. And I need to talk a little bit about special forms. Special forms are the syntactic scaffolding for your language. So these are all the keywords that you know from a language like Java. So the if is a special form, and so is while. Import, scopes, protection, control flow, anything using a keyword is a special form. And that's what you do when you learn a new programming language, is you learn the rules for the special forms. When you learn Java, you learn about the if statement, you learn about the Boolean short circuit option, you learn about the else, you learn about the dangling else problem. Those are all characteristics of that if special form in Java. And outside Lisp, in languages like Java, special forms are limited to a specific use. You can only use the if statement to do decisions about things, and that's it. They look different from other things. You can't build something that looks like the if statement. In fact, you can't build new statements in Java. You can build functions and methods, but you can't build new statements. Some of the special forms have special semantics that are not available to you, like the if statement and the way it does short-circuit Boolean evaluation. That facility is just not available to you as a developer. And because of that, they end up hampering reuse in a lot of situations. And I'll talk more about that in a second. So what's so special about Lisp special forms? In Lisp, they look like everything else because it's just a list. Remember, everything is just a Lisp data structure. And special forms in Lisp may have special semantics available only to you as a developer. So the language designer is actually giving you more power than they've taken for themselves. And the really nice thing is they can be augmented with macros, and that's where the real power comes from. And I'll show you an example of a macro in just a second. And so here are the forms in Clojure. Functions are actually lists. Operators are actually lists. Method calls are lists. And, well, you get the idea here. Everything is a list. It's all the same kind of thing. So why is this so important? Why do I keep ranting about this? Special forms are easier to understand individually. That's why they were created in programming languages, because they're easy to understand. There's a concrete set of rules about how if works. But then you get a whole bunch of things that have concrete rules, and you mix them all in together and have them start interacting with one another, and you get combinatorial complexity when you have a lot of special forms. And to deal with that complexity, you start categorizing things, and when you start categorizing things, you end up with things like design patterns, which does not exist in the Lisp or Clojure world. So what's the alternative to that? Because what design patterns do for us in Java is help us build reusable code and help us isolate and get rid of duplications and things like that. The alternative in the Lisp world are macros. Let me show you this, how this works. So for example, let's say that I want to build a swing application in Clojure. And I've got a frame, I want to add a panel to it, I want to pack the frame, and I want to set its visible property to true. That's how you'd write that code in Clojure, but it's annoying that that frame thing keeps showing up over and over again. That duplication is annoying. And so we can stamp that out. I'll create a do to frame and then do all these things to it, say it once, and then that do to actually returns an expression so you can do some other stuff to it. So we've used a macro there to eliminate this duplication and got it down to just one of them, and now we have a better context for doing that. Do to is a built-in macro in the Clojure world. There are actually a bunch of macros built in the Clojure world. A lot of the features in Clojure are implemented with macros. How can you tell which ones they are? You can't, and that's the point. Let me show you an example of a simple macro. So let's say that I want to say, when x is true, then print this stuff. Turns out that when does not exist in the language yet. So I can build it by creating a macro. This def macro says take in a test and an optional body. That's what the paren means, is the rest of this is optional. So I can take in an optional body. And the return of this macro returns a list that says, if test, then construct a list that consists of the body. That's what cons does, construct a list. But you'll notice the little tick in front of if and do there, because when I actually expand this macro, what it's going to expand to is if x, then do print line x is true. But notice what translation has happened there. Basically, when it gets into this macro, it takes in test. Okay, it's going to return a list. What is this? This is a list. It's going to return a list that has if as the first element, and then the test, that's my parameter, and then it's going to construct a list with the word do and then the body. Notice that metaprogramming in Clojure is just programming. In languages like Ruby or Groovy, you have to switch to a different syntax to do metaprogramming. You have to learn about the expando meta class, or in Ruby you have to learn about the eigen class. In the Scala world, you have to learn about implicit cast and all that other stuff. You don't have to learn any of that in Clojure, because there is no metaprogramming in Clojure. Programming is metaprogramming in Clojure, because Clojure programs are Clojure data structures. For example, there is only one mechanism in all of Clojure that does decisions about things, and it's called if. Every other Boolean thing in the Clojure universe are macros built on top of if. One place to make sure that truthiness is understood, and then build every other facility in the language on top of that one trusted thing. That happens all over the place in Clojure. So a lot of what you look at as keywords in Clojure are actually macros. So that double dot thing I showed you is a macro, syntactic sugar. Anytime in Clojure you have something that's ugly, you can macro it away and make it pretty again. And that's really important because what we have been doing for the past 30, 40 years is taking some kind of problem, some kind of business problem, and translating that problem into Java. And sometimes that's not a friendly translation. You try to do the opposite in Clojure. In Clojure, because the language is so bendable, you actually bend the language toward the problem, not the problem toward the language. So it's really characteristic in Clojure to actually build up toward your problem using macros and other sorts of syntax and language, rather than just purely try to translate your problem into the only building blocks you have. So here's the analogy I'm working on. I may be hampered by my age, so we'll try this out. So Java is like a porcelain doll, where you can't move any of the limbs. It's just a porcelain doll. Groovy and Ruby are like the superhero figures, where you can bend some of the joints, like the elbows and the wrist. And Clojure is like Gumby. Do you know what Gumby is? This is my problem, is a lot of people don't know what Gumby is. Gumby is this plastic doll that just has wires in it. You can bend him in any shape that you want. That's what Clojure is Gumby compared to a porcelain doll. And that's why this is so important. This is, in fact, people ask me, what kind of projects would you use Clojure for? And the answer is the nastiest, hardest, toughest kinds of projects possible. Because it's those projects where you need the ability to mold your language toward your problem, not vice versa. So actually the two most sophisticated projects we have going on in the world right now are both Clojure projects on purpose, because we think that that's the only way those projects could be done. So that's why you endure all these parentheses. The parentheses make this possible to do this kind of metaprogramming. They also make a lot of other handy things possible. So one of the things that you learn when you learn Java, you know, there's a chart that has operator precedence, where the multiplication happens before plus, etc. That chart doesn't exist in Clojure, because everything is in prefix notation. You are writing it in the abstract syntax tree. You're not having to translate it anywhere. And so, for example, plus, you can say plus with 2 numbers, but you can also say plus and have 40 numbers there, because you're just adding them all together. So another thing that's interesting about Clojure is a strongly functional language. So how is that different from what you're used to in the object-oriented world? And how do you achieve reuse? So in the object-oriented world, the way that we achieve reuse is we create a network of classes that communicate with one another with messages. We find a piece of this that works really nicely, and so we isolate that off and package it up and package that as a reusable class. It's not coincidental that in the Gang of 4 design patterns book, every single design pattern has a class diagram. That's just the way you solve things in imperative object-oriented languages. Functional languages are not after that. Functional languages take a different approach to this. What functional languages have done is taken a few data structures. Remember I said that functional languages prefer a small number of data structures and a lot of operations on them. What they do is build machinery that understands those few core data structures. And what you're expected to do is take data plus customization in the form of a higher order function and pass into this machinery and have it work on that and do transformations for you. This is an example of what I call coarse-grained machinery to get stuff done. So what they've done is taken really common abstractions for things that you do for things like lists and maps and written generic versions of operations on them. So for example, if you have something like a list, one of the operations that you might want to do on that list is say, I want to be able to convert this list into a single element. So let's say, for example, I wanted to sum this list. One of the ways to sum this list is to say, take the first element, add the second element onto it, and make that the new first element, and then do the same again over and over. And if the operation you're using to do that is plus, then what you're left with is the sum of that list. That's known as a fold or reduce in the functional programming world. You're reducing that down or folding it down to a single value. Another one of these transformations, common transformations, is take a list and return me a subset of that list, which is a filtering operation. Another one of these operations is take some existing list that has values in it and then map a function onto each one of those, yielding a brand new list of items. These are really common things that pop up all the time, and of course they have optimized versions of these in Clojure. This will also change the structure of your code. So I want to do another one of these transformation exercises, and this one's actually a little more sophisticated. This is Apache Commons index of any. What this is supposed to do is you give this a string and some characters, and it will tell you the beginning index of where those characters start. So for example, here, B and Y, it looks like B is in the 3 position, so that's the first one of the 2 that show up. It's in the 3rd position, so that's what this thing is supposed to do. And here's the implementation for it. And so let's collapse this down to Lisp. First thing we'll do is simplify the corner cases. The corner cases up at the top are the is empty. Both those empties actually are handled by my when, or will be handled by my list comprehension in a second. So we can get rid of the edge cases. We can also now strip out all the type information because we don't need type declarations anymore. We will now come in and replace that for loop, the internal for loop, with a when clause that basically says when you find one of these search characters, then just return it. Now I'm going to add a list comprehension to get rid of this for loop. Now I'm going to replace it with something that says for, which is just poorly named in my opinion because it's not a for loop, it's actually a list comprehension, which is kind of a Swiss Army chainsaw of doing things with lists. What you can do with a list comprehension is basically say for a collection, here's an input format and some values and what you want it to return. And so I'm going to say for each index and character and index, then in my index string, then return the index when I find that character. And now I'll Lispify this guy. This is now index filter. It takes in a predicate and a collection. The predicate is a higher order function that tells how to decide if it's in the collection or not. When that predicate's true, then it's going to look at each index and element in the index collection, and when that element is true, it's going to return that index. But now that we've done that, okay, sorry. Oh, you can't read Lisp code that fast yet? That's shocking. The list comprehension is the trickiest thing here. Basically what that's saying is what I want as an input pattern is an index and an element. And the collection I'm doing this for is in the index collection. When is a flag. You can put when or if not, or some of those things to determine when those things end up getting filtered in or not. And then the return value that you ultimately want of those things is the index.
So when actually, I thought it's just an if statement kind of. I didn't realize it returns value.
Well, this is actually doing a filtering for me. This is doing a filtering operation. When this is basically a predicate that says when this is true, then I want that to execute. So it's not actually a for loop at all. It's a list comprehension. It's basically a way to apply a bunch of logic to a list in bits and pieces. But now that we've got that, which version is simpler? The imperative version has 18 moving parts. The functional Clojure version has 4 moving parts. So the Clojure version is actually simpler in terms of amount of code and number of characters, and yet it's more general. The Java version only works on strings. This works on any sequence. So if I want to say index filter, give me the number of heads out of a string of head and tail flips, it looks like the heads all show up at 2, 4, 8, and 9. Here I'm saying is give me the first Fibonacci number that's greater than 1,000. So give me the root of the first Fibonacci number that's greater than 1,000. Turns out it's 17. 17 is, comes out, Fibonacci of 17 is a little over 1,000. So the imperative version searches only strings, whereas the functional version searches any sequence. Imperative version matches only characters, whereas the functional version matches any predicate. You pass the predicate function in to determine what the match criteria is. The imperative version returns only the first match. The functional version returns a lazy sequences of all the matches. So that's another thing you get from most of the sequences in Clojure is they're all lazy, meaning that they evaluate the first element and then don't evaluate the rest of them until you ask for them. So it's as efficient as possible. It generates as few values as it needs to, but then you can ask for more, and it'll lazily generate those values for you as you need them. And so here, for my index, what I'm doing here is saying, well, give me the first one, but then I can say, okay, well, give me the next one and the next one and the next one. So it's actually more general and more powerful than the imperative version. And this is true in a lot of functional code, and particularly in the Clojure world. You really want to get to general solutions to things, and having dynamic typing and higher order functions allows you to do that. So before we get too deep into this, let's start talking about state and concurrency, because that's one of the reasons you came here, is because you heard Clojure had this really wicked cool stuff around concurrency, and it's true, it does. But let's talk about data structures for a second in the Clojure world. Data structures in the Clojure world are immutable, which may make you frightened for performance, because you're used to a language like Java, where immutability is a second or third class citizen at best. So in Java, if you have something like a mutable data structure and you want to change it, you have to create a brand new immutable data structure with all the same values and there's a few separate values. But that's not true here, because if you can assume everything's immutable, you can share the common parts of those data structures when you create new ones. Everything in Clojure is immutable. You change things by applying a function to it to move it from one state to another. All of the persistent data structures maintain performance guarantees in Clojure, so they're all very high performance. You also get full fidelity old versions. Clojure never deletes anything, because everything's immutable. You can't delete things if they're immutable. And so Clojure doesn't delete things. So how would that work with a linked list? So if I have my list and you have your list and they happen to share some common terms, this is perfectly okay, because neither one of us can change any of the things we point to. It's perfectly safe to share this data structure if you can assume that every one of these elements is immutable and can never be changed or deleted. So that works perfectly great with lists. What about more complex things like trees? You can do the exact same things with trees. In fact, there's some really deep computer science in Clojure based on some studies of red-black balanced trees. That's how this is implemented underneath. So if you have your part of a tree and there's another part of a tree, you can actually share a lot of that data structure because all the values are immutable. This is an example of bit partition tries. This is an example of doing 2-bit partition tries, which is too slow for practical purposes. What Clojure actually implements underneath is a 32-bit red-black balanced tree to store all these data structures. And log 32 is fast enough. That basically means that you get to the results really fast, because it's a really flat data structure rather than a really deep data structure. So that's the trade-off, is flat versus deep. This is all internal details. You never have to care anything about this, but this is how he can maintain performance guarantees and have immutable data structures internally as well. He's determined that log 32n is fast enough to be able to find things as you traverse through this tree. The other interesting thing that Clojure has done around state is identified what makes concurrency so hard in Java. It's actually surprising. The core, the root of the problem, if you go all the way down and find the criminal that makes threading so hard in Java, it's variables. Because when they created variables in Java, they weren't thinking about concurrency and multi-threaded situations. They were always thinking about this variable owns this for all of time, and nobody else will ever interfere with this value. The problem is it's convoluting several different important concepts, basically this idea of identity and state. Because a variable in Java holds on to the identity and whatever value happens to be there as well. And it's hard to predict when that's going to change, and it's hard to logic about that over time. What Clojure has done is said, you know what? We can fix this. So what Clojure has done is says everything is immutable save one thing. There's one thing in Clojure that you can mutate, and it's a reference. So you can have a variable that points to a reference. That is its identity. That reference is its identity, and at some point in time, it points to some value. At some snapshot in time, that is its state. The identity's value at a point in time is its state. But what Clojure has done is said, you know what? If I can take over that, if you'll let Clojure manage that for you, then Clojure can manage all of threading for you. This is the core. This is the central place where if you'll let Clojure handle assignment for you using its functions, that it'll handle all concurrency issues for you. That's the way that this works. So what they've done is kind of remap the idea of variables. A value is an immutable data in some persistent data structure somewhere. Identity is a series of causally related values over time. State is identity at some point in time, and time is relative. It's before, it's simultaneous, it's after. But ultimately, and this is a campaign that Rich has been on, we've got to start adding time awareness into our code. We can't ignore time anymore, because if you talk about some value, it's meaningless unless you talk about when that value is applicable. Because values, identities change over time. They point to different values over time, and so you have to know the time to know what value that identity has. And that's what he's really done, is created explicit semantics around that in Clojure. And so what happens in Clojure is identity is a succession of states. You move from one state to the other. You change from one state to another by applying a mutating function that moves the reference from one value to another value. It doesn't change the identity. It just moves what it points to from one place to another. Then at any point in time, observers or perception memory can look at the state of that thing, which is the identity and the value at this point in time, and see what it is. So this is this idea of a unified update model. So what you do is you have a function that changes the state from a reference using that anonymous function for its value. Snapshots are always available, no user locking and no deadlocks. Writers never impede readers, never a deadlock, never a concurrency problem, never a collision. In fact, you can also, with software transactional memory, say, I want all 4 of these variables to get mutated or none of them. But you can't do it all in Java now. There's no transactional semantics around variables at all, but there is in Clojure. And that's really software transactional memory, which is the next thing I'm going to talk about. Because in software transactional memory, what happens is moving that pointer from a reference to reference one value to another. Clojure does that within a transaction, which means it can do many variables if you want within the same transaction, because it's managing all that. That's exactly what this image is showing, is that you can actually tie several variables together and have them work in lockstep. Clojure will go back and retry things that it can't achieve. You can set retry limits and other kinds of things, just like a transaction engine would. This is the syntax for doing this, and the syntax is actually kind of anticlimactic because it's just pretty simple and straightforward. So here I'm defining messages, which is a variable that points to a ref. And that ref is currently empty. It's pointing to an empty list. So I now have messages which points to an empty list. If I want to find out what's in messages at any point in time, I can call the deref function on messages and see what's in there. This is such a common operation. There's a special syntactic sugar. If you just put @messages in front of it, it will dereference that message for you. So let's talk about altering a message. You can use the alter function like this, where I have a reference and an update function. What that's going to do is take the old value and then use that apply method to update that to the new value. So this is what that looks like. Let's say you wanted to update a message. You had a messaging application or something like that. Here's a defined function add message, taking a new message. And what I'm going to do is alter messages, that's my reference to my list, can join this message onto the end of it. So add another message onto the end of my list. But you'll notice do sync right here. If do sync is not there, Clojure won't execute this code. You'll get a runtime error saying you're trying to mutate something outside a transaction and I won't let you. You have to have do sync there. That's what kicks off the transaction, but that's it. Now you've got software transactional memory. Questions about that? It's a really simple mechanism when you see it. The underlying implementation details are horrifically complex, but you never see that. Just like the garbage collection algorithms in Java are horrifically complex, and you never see that either because you're working at a higher level of abstraction.
That's a runtime message?
It's a runtime message, yep.
So you get the full ACID properties?
You get everything but D. So you get atomic, consistent, isolated, but no D because it's memory. But you do get, of the 4 transaction characteristics, ACID, atomic, consistent, isolated, and durable. You get all but durable because it's all happening in memory. But it is a completely ACID except for the D in memory. Very super powerful mechanism in Clojure world. So let's look for a little bit about what data looks like in the Clojure world, because Clojure really likes things that are in maps and really very lightweight data structures. But you can map back and forth between this world and the Java world. So let's say, for example, I wanted something that looked like a class, the data parts of a class. This is basically creates a name type with slots. So I can now have define a foo and construct a new foo object there with a positional constructor. I can now, if I want to get values out of f, I can just use the keyword against the data structure and it'll return the value. This is true in maps as well. I can also ask it what class you are and it'll tell me what class it is. I can also ask it what its superclasses are, and here are a bunch of things that Rich has automatically added to things, classes you create in Clojure to make it much easier to deal with, like persistent collections and other things like that. But you can also do this in maps, and this is a kind of a more typical way to do this in the Lisp world. So here, for example, is some information about Stu Holloway, who wrote the very first Clojure book, where I'm creating this map that's basically a nested structure. What does this look a lot like? It looks a lot like JSON, doesn't it? This is a really powerful transport mechanism back and forth, particularly if you have Clojure and ClojureScript on either side, because you're actually passing real code back and forth without having to serialize and deserialize into JSON. It's the real data structure, which is kind of nice. But it's easy to map between this and something like JSON. You can get keyword access, so if I have Stu, I can say, give me the last name of Stu. A keyword becomes a function on the collection. This is just syntactic sugar in the Clojure world. I can also get nested access with this the syntactic sugar little arrow guy here that says, give me Stu address city, so that's actually digging into this collection. If I want to do an update here, I can say do an update for Stu and create a new, give him a new first name, Stuart, instead of Stu. When I do this update, notice I'm not doing this in a transaction. What it's doing is returning me a new data structure. So this is immutable, just like you'd expect immutable. It's sharing all the common parts, but it is returning a brand new data structure. And the old one is still there because nothing ever goes away. And you can also do nested updates as well if you want. But you can do the exact same thing on top of records if you want, which are basically classes. So here's the same thing constructed in an object-oriented fashion. But even if you have this object structure, you can still use the same keyword access to get things out of maps. You can still use the same nested access thing to get things out of deeply held collections. And you can also do the update the exact same way you did it before. This is part of this easy mapping between Java and Clojure. Clojure likes maps, Java likes classes. You know what? We'll just map them back and forth between each other and let them very seamlessly move back and forth. So you can't add methods to it. Well, actually you can in here, but you're actually then creating a class. So you create a new class, you create a bunch of functions that are associated with that class. But that's actually a pretty rare thing because you're not really the only reason you do that is to pass that back over to Java because it wanted a class for something. And you could actually build it as a map, and then as you pass it, it'll coerce it into a class. But you're right, there are no methods on this. This is just the data part of it. So Clojure is a function-based language. Everything is function. So the idea in Clojure is you have a collection of functions. You can also have namespaces. So you can think of a namespace almost like a package. There's a named collection of functions. Within the namespace, you can actually have functions that are private to that namespace. If you do def n minus, it's private just to that namespace. You can also have this thing called a protocol, which is very much like an interface. So the idea in Clojure is, instead of doing classes, what you do is define a namespace that has a protocol in it that defines the semantics of how you're going to call functions. That's actually implemented by functions underneath inside that namespace. And so you have these kind of coarse-grained collections of functions that are namespaced that you can execute and do things with. That's the way a Clojure program looks like. That's the structure of Clojure code. It's kind of like packages, classes, and methods in Java, except that we just eliminated the classes part. And you pass around data as parameters instead of being passed around as part of the object. So, what's cool about Clojure? It's a really highly expressive language once you get used to reading Lisp. And it doesn't take that long. In fact, if you want a fun way to kind of get hooked on writing Clojure code, go and download the Clojure Koans. It's K-O-A-N-S. A lot of languages have these cones now, which are these little Zen puzzles that basically are just ways to exercise syntax. So if you download the Clojure cones, you run it, and it'll give you a little puzzle, and you fill in with the code to make it work, and then it'll run, and it'll automatically pick that up and then give you the next one. So this is the Clojure equivalent of potato chips, because you start doing this, it's like, okay, just one more. Okay, I'll just do one. Oh, I can get that one to work. One more, and then before you know it, it's 2 a.m., and you've eaten a whole bag of Clojure. Really super expressive language once you get used to reading the syntax, and it really doesn't take much time at all. Really good seamless Java interop. That's one of the goals of Clojure is really, really good Java interop. Heavily functional, of course, and a really advanced concurrency story. The other thing that I would point you to as a kind of a mind-bending exercise is, so Rich Hickey is the guy who created Clojure. He's here, wandering around. He's doing a keynote tomorrow. The project, the big top secret project he's been working on for like 2 years is this thing called Datomic, which is an atomic with a duh in front of it. Datomic is an immutable database. Think about that for a second. It uses all this Clojure stuff and software transactional memory, but when you put stuff in Datomic, it doesn't go away. Which may scare you because it's like, well, then it's just going to grow forever. But I've got a question for you. How many times does the number 9 appear in your relational database? That's a stupid waste of space when you could just store 1 9 and then have every 9 that needs it point to it, because 9 never changes. 9's a fact. So that's how Datomic can store basically an infinite amount of information and never throw anything away, because it's immutable, and you can rely on immutability to do this. So, but thinking about that, so in Datomic, schema and data use the same syntax. So one of the really nasty problems in the continuous delivery world is, let's say you got your code and you got this database schema, and now you want to roll back to a previous version of your database schema. We have all these migrations and other crazy mechanisms to do that. In Datomic, you just point it to an older version of the database, because every version that's ever been is still there. There's no migrating back and forth, it's just there. It's always been there. It will always be there. That's the point. Now you're going to have to start answering this question at your company. Why, when you're using that relational database, are you destroying valuable company data every time you're doing a destructive update? The reason you're doing that is because hard drive space is really expensive and really critical resource, and we want to do as much as we can to maximize that. Oh, wait a minute. That's not true at all. A lot of our architectural assumptions are based on 20-year-old ideas, like we need to maximize storage space as much as possible, so reuse that space. Well, that's a dumb idea now when we have as much space as we want, and there's huge value to keeping that historical data that's happening in that database. So that's a good example of the kind of radical rethinking that becomes possible when you have a language that has really, really advanced capabilities and has some really core key changes implemented down at the very bottom. Once you listen to Rich talk a lot, you realize that Clojure is not so much a programming language as a vision for how to write software that you could only implement by writing a new programming language called Clojure. And that's exactly what Clojure is. So I'm out of time. I'm actually 5 minutes over. I apologize for that. If you've got other questions, I'll be happy to answer them. And of course, Rich is here. He's the source of all knowledge in this universe. You can chase him down and congratulate him on Clojure and ask him some questions as well. Thanks very much for coming, and hope you enjoyed it.